Now we are going to solve the third problem in the chapter 9. Look at that. Here we are going to see about the hydrogen atom. In hydrogen atom, the electron that is revolving in the first orbit, only one electron it is revolving in the first orbit. So the energy level diagram of the hydrogen atom is drawn here. The electron which is revolving in the first orbit, its energy level is called ground state. When the electron it is in the ground state, that is in the first orbit, by the time the energy of the electron is minus 13.6 electron volt. Okay. Now this electron that is excited by a radiation. Okay. So we are sending the energy from outside, that one will be absorbed by the electron. After absorption, the electron will be excited to a particular level. The incident radiation, its energy to be calculated, its wavelength is given. The wavelength of the incident radiation on the electron is given, lambda is equal to 97.5 nanometer. The question is, you are asked to find out the principal quantum number of the excited state. After absorption, to which level the electron will be taken to the particular level. Whether that electron will be taken to the second one or third one or fourth one or fifth one, that excited level principal quantum number to be found out. And then finally you are asked to find out the total number of possible lines in emission spectrum. How many number of transitions are possible, that should be found out. Are you clear? Two things to be found out. So how to start the problem, that is the question now. First we will calculate the energy of the incident radiation. Wavelength is given. With the help of the wavelength value, we are going to find out the energy of the incident photon, energy of the incident radiation. How to start? Lambda. Lambda it is given in terms of nanometer. 97.5 nanometer is equal to 97.5 into 10 to the power of minus 9 meter. So it is converted into meter. So what is the formula to calculate the energy? E is equal to h nu is the formula. H into, instead of nu we can write it as C by lambda. So this is the appropriate formula. The next step, H must be substituted. 6.6 into 10 to the power of minus 34, and then into C value 3 into 10 to the power of 8 whole divided by lambda value 97.5 into 10 to the power of minus 9. Wavelength is substituted in terms of meter. Are you clear? If all values are calculated, you will get the answer in terms of joule. But here the energy value to be calculated in terms of electron volt. So what we have to do? 1 electron volt is equal to how much? 1.609 into 10 to the power of minus 19 joule. So here it is, the value it is in terms of joule, but the value to be converted into electron volt. Therefore this value to be divided here. 6.6 into 10 to the power of minus 34 into 3 into 10 to the power of 8 whole divided by 97.5 into 10 to the power of minus 9 into this value to be written in the denominator. Only then the conversion is possible. The final answer will be, you will be obtaining in terms of electron volt. The finally you will be getting the answer is 12.74 electron volt. So this is the energy of the incident radiation. Are you clear? That is going to be used up for exciting the electron. So this is the energy of the incident radiation. Make a note. Are you clear? Just we have to find out the energy of the incident radiation. After absorption, we have to find out to which level that electron will be excited. So for that what we have to do? Next we have to find out the difference between these two. Are you clear? Find out the difference between these two. You will get one value. No? With the help of that we are able to obtain the to which level, to which excited state the electron will be excited. That could be found out. Okay. So we will do the step 2 later. So therefore this one could be taken as step 1. Are you clear? Next we are going to see the step 2. Okay. Now we are going to find out to which level that electron will be excited. That should be found out. Now we can use this simple formula. Energy of the incident radiation is equal to energy of the particular orbit. Energy of the particular level can be written as En. We don't know the value of n, but we know the value of the ground state of the electron, energy of the first ground state of the electron. So by using this expression, we are able to find out En. So how will you calculate En? En is equal to energy of the incident radiation plus energy of the first state. Are you clear? Energy of the incident radiation was already calculated in the previous concept. How much? 12.74 plus energy of the ground state is minus 13.6 electron volt. Both are in electron volt. So after subtraction, 12.74 minus 13.6 electron volt, after subtraction, we will be getting the answer is minus 0.86 electron volt. Are you clear? So this is the energy of the which orbit? A particular orbit to which the electron is excited. Still we don't know the principal quantum number. So what we have to do? We have to use the expression En is equal to minus 13.6 divided by n square electron volt. This formula can be used to find out the n. So here energy of the particular orbit, is it clear? That could be found out. Here En is found out. So how will you calculate? En can be substituted here. Minus 0.86 electron volt is equal to minus 13.6 divided by n square electron volt. Both of them can be substituted. Minus sign can be cancelled. Electron volt can be cancelled. Now we can cross multiply the value. N square is equal to 13.6 divided by 0.86 can be substituted. So n square, if you calculate, roughly you will get the answer as approximately you will get the answer as n. N square is equal to 16. Therefrom we are able to get the value 4. It shows that if you give this much amount of energy, how much? 12.74 electron volt, that is the energy of the incident photon. No, if you give that much amount of energy, the difference between these two, are you clear? The difference between these two level is how much? 12.74. So after absorption, that one will go up to which level? That fourth orbit, that is the fourth energy state. This is 1, this is 2, this is 3, this is 4. So if you supply the incident radiation with the wavelength of 97.5 nanometer with the energy of how much? 12.74, the electron will be excited to which level? The fourth level. So that is the meaning of the sentence. Are you clear? So here the energy of the incident radiation is how much? 12.74. That is the energy of the incident radiation. If you give that much amount of energy, so it will be raised up to this level. That is the meaning. So finally it is reaching the energy state whose energy value is minus 0.86 electron volt. That is equivalent to the energy of the fourth state, fourth excited state. Okay. Now we are going to calculate the number of possible transitions. First, we will calculate physically, okay, how many number of possible transitions are possible. Here, now the electron, it is excited here. So, what are the possibilities? Tell me. First, it is able to get down from fourth orbit to first orbit. So, this is the first possibility. Next possibility is 4 to 3. Okay, 4 to 1 is possible. And then 4 to 2 is possible, 4 to 3 is possible, 4 to 3 is possible, and then 4 to 2 is possible. Are you clear? What are the other possibilities? Sometimes the electron may be here. Now if it comes here, the next possibility is 3 to 2. Are you clear? The next possibility is 3 to 1. So these are the other two possibilities. The last one is when it comes down, the one more possibility is when the electron is here in the second orbit or second state, it is able to come down. So how many number of possibilities are there? 6 possibilities are there. So roughly we have worked out and it is shown physically. But this one must be proved with the help of the formula. So here the formula is n is n into n minus 1 whole divided by 2. So this is the formula. So here n, what is the value of n? At which state that electron is there? That is in the principal quantum number 4. So n value is taken as 4. So substitute 4 into 4 minus 1 whole divided by 2, 4 into 3 divided by 2, cancel, you will get 6. Therefore, how many number of transitions are possible? 6 possible transitions are there. Okay, so this is the final answer. So this is proved with the help of the formula. That one is shown in the form of the clear energy level diagram. So both are similar. So it depends on the n value, number of possible transition, that one will vary. Okay, for that we have to use the permutation combination formulas. Okay, thank you.